Vashaw, tell us about twisting of universal quantum groups and comodule algebras.
Great. Yeah, so thanks for the introduction. Thanks to all the organizers for this opportunity to speak. So this is a joint project with Hongji Wang, Van Nguyen, Charlotte Ure, Padmini Virafin, and Xingting Wang. And in some ways, this talk is going to be a sequel to the talk that Van gave yesterday. So she talked about some of the results from our first joint paper together. I'll be focusing on some results from our second and third papers. But I won't assume that you remember everything from that talk, so I'll repeat a few of the definitions and concepts. Right, so just a quick outline. So first I'm going to say a little bit of background. So of course I want to say something about the words in the title. So what is a universal quantum group? What do we mean by twisting, or some more generalized versions of twisting? And what's our motivation for studying this? The second main part of the talk is going to be some abstract results about properties of algebras which are invariant under the kinds of twists I'm going to talk about. And then I'm going to spend maybe the last third of the talk focusing on some concrete applications, which are to superpotential algebras and the universal quantum groups of superpotentials. Okay, so some basic setup. So throughout the whole talk, K is going to be a field. I don't think I need algebraically closed anywhere, but if I do, I'll probably say it. Typically, if I say A, I'm always assuming it's some n-graded algebra. So usual graded algebra properties. Usually, I'll also assume that A is connected, so the degree 0 piece is just the field. Usually, H is going to be a Hopf algebra, so it has this additional structure of a co-multiplication from H to H tensor H, a co-unit from H to K, and an antipode map from H to H. And okay, so of course, using this Hopf algebra structure, the category of comodules for H or the category of modules is always a tensor category. So the kind of big picture idea for this project is I want to understand properties of a graded algebra A by understanding how Hopf algebras coact on A. So just to kind of recall, if you have a Hopf algebra, then a coaction means that A is going to be an H comodule. So I have a comodule map from A to A tensor H. It's co-associative and co-unital. And more than that, A is an algebra in the category of H comodules. So the multiplication map is an H comodule map. So this is what I mean by coaction. And in general, I mean, of course, in general, many different Hopf algebras might be coacting on my algebra, but I want to study this in some kind of systematic way. And that's the point of introducing this universal quantum group, which was originally introduced by Menin in the 1980s. So for a lot of the results that I'm going to mention in this talk, maybe you could replace universal quantum group with arbitrary Hopf algebra that's coacting on A. But in order to kind of package all these results up together, I'm going to state them on the level of the universal quantum group. So what is a universal quantum group? So this is just defined as a Hopf algebra. So there's a left version and a right version. So the left universal quantum group is going to coact on A on the left of course, in a universal way, by which I just mean if you have any other Hopf coaction on A by some Hopf algebra H, then that coaction factors through the universal quantum group on L of A. And of course, there's nothing special about the left. I can also define the right universal Hopf algebra. And I can also, I don't need to use Hopf algebra necessarily. I could also just replace everywhere I say Hopf algebra by algebra. In that case, I get I'll denote these universal coacting bialgebras by end L of A and end R of A. Okay. So it's something you might worry about. Do these exist? In general, they don't necessarily. But if A is finitely graded, then they do exist. It's a result of Agore, Gordienko, Vercrusa.
Can I ask you a question?
Sure.
So your algebra is grade A, but H is not necessarily grade A?
Exactly. And yeah, that's a good point. I should also say, I do want to require here that the coaction respects the grading of A. So the grading does play a role, but I'm not assuming, I think it's a result that you could put a grading on the universal quantum group, but it's not part of the definition. Right. Yeah, thank you. Other questions? Okay. Great, so here by locally finite, I just mean each graded piece is finite dimensional. And okay, so that's a little bit abstract, so I want to show you a concrete way of writing down the universal quantum group, or at least a concrete way of writing down the universal bialgebra in the special case that you have a quadratic algebra. So in that case, you can define the bullet product between any two quadratic algebras. It's just an algebra generated by the tensor product of the generators of both of them, and you quotient out by relations, which are the relations of A, tensor the relations of B, and then just swap the middle two factors so that you actually get something in A1 tensor B1 tensor A1 tensor B1. Right. Then the universally coacting right bialgebra is just the bullet product of A with its Cazul dual, right, which is just, of course, quotient out by the perpendicular space to the relations of A. And okay, and the left universal bialgebra is just the right universal bialgebra of the Cazul dual. So just take the bullet product in the opposite direction. And in order to upgrade from the universal bialgebra to the universal Hopf algebra, you use the Hopf envelope. So in general, the forgetful functor from Hopf algebras to bialgebras has an adjoint, which is the Hopf envelope, which just satisfies the expected universal property. And then the universal quantum group is just the Hopf envelope of the universal bialgebra. Okay, so I could write down the universal bialgebra by generators and relations very easily. Okay, Hopf envelope still may be a little bit vague. I promise that later in the talk, I will actually write down generators and relations for at least one universal quantum group. But one example I want to give first is, so this isn't quite a universal quantum group, but it's close. So OGLN coacts naturally on just a polynomial ring. And if you write down the relations for the right universal quantum group, then you get kind of half the relations of OGLN. So OGLN is a quotient of this. And actually, there's a version of universal quantum group where instead of coacting on one side, you want compatible coactions on both sides due to Chirva-C2, Walton, and Wang. And in that case, you actually get OGLN as the universal doubly acting quantum group for the polynomial ring. Okay, so in general, I'm going to say that two Hopf algebras are Morita-Takeuchi equivalent, just if their comodule categories are equivalent as tensor categories. And I'm going to introduce another term, basically because when we were working on this paper, we realized we were saying everywhere, suppose A1 and A2 are algebras, so that their universal quantum groups are Morita-Takeuchi equivalent. So in order to kind of simplify that, we call this quantum symmetrically equivalent. And the main question that I'm trying to answer in this talk is, what properties of A are really properties of its quantum symmetric equivalence class? So to say a little bit more about this, I need to get more into the details of how do Morita-Takeuchi equivalences work. So a left Galois object for a Hopf algebra is just going to be a left comodule algebra, such that when you take this composition, you get a linear isomorphism. And okay, you could also define right Galois objects. And okay, so a bi-Galois object between two Hopf algebras is just going to be one which is a left Galois object for one and a right Galois object for the other. And then it's a classical theorem of Schoenberg that Morita-Takeuchi equivalences always come from bi-Galois objects. So there exists a Morita-Takeuchi equivalence if and only if there's a non-zero bi-Galois object between two Hopf algebras. And a special case of Morita-Takeuchi equivalences, which I think we saw in Van's talk yesterday, are two co-cycle twists. So two co-cycle is just an invertible map in the convolution algebra, which satisfies these two co-cycle conditions. And if you have a two co-cycle sigma, then there's a way of twisting the multiplication of H, which is the two co-cycle twist. And H sigma is always Morita-Takeuchi equivalent to H. And you can say what this means on the level of bi-Galois objects. So it's so two co-cycle twists, it's as a subset of all Morita-Takeuchi equivalences. Okay. So I'm going to recall a result from Van's talk and rephrase it into some different language. The philosophy of non-commutative projective geometry to study quadratic algebras or graded algebras is to think of the non-commutative projective scheme associated to A as a category built out of the category of graded modules for A, which plays the role of coherent sheaves on a non-commutative space. So in other words, this non-commutative projective scheme is an invariant of the graded module category of A. So from a non-commutative projective geometry perspective, you really only care about A up to graded module category equivalence. And it's a theorem of Artin, Tate, and Vandenberg, who I think did it in the connected case, and Zheng generalized this to much wider context. But two connected graded algebras, A and B, are graded Morita equivalent if and only if there's a graded automorphism such that what we call the Zhang twist of A is actually isomorphic to B. And this is the definition of a twist that Van showed in her talk, where you just twist the multiplication of A by this graded automorphism. And so this is the result that Van showed in her talk, but I'm putting it in some different language, which is if you have a graded automorphism of A, then A and its Zhang twist are quantum symmetrically equivalent. So, in fact, as we saw, this equivalence is not just an arbitrary it's not an arbitrary Morita-Takeuchi equivalent. It comes up as a two co-cycle twist. So in other words, just to rephrase this, equivalence of graded module categories on the level of algebras gives you, if you look at what it does on the level of their universal quantum groups, it gives a tensor equivalence of the comodule categories. Or one final rephrasing of this result is quantum symmetric equivalence is an invariant of non-commutative projective schemes. So this is our first hint that quantum symmetric equivalence is an interesting equivalence relation from the perspective of non-commutative algebra or non-commutative projective geometry. So in order to get to say some more specific results, I'm going to specialize the class of algebras that I'm focused on. So we call a graded algebra A Artin-Shelter regular, or I'll abbreviate this by AS regular. It has finite global dimension, and there's some integer L, so that if I take the graded X of K with A, then this is just K shifted by L if I is equal to D and zero otherwise. And here K is just the trivial module, which is A quotient by its higher degree pieces. Often, if you see this definition written down, most of the time it'll also have an assumption of finite GK dimension. I'm not going to require that in this talk. If I want to say finite GK dimension, I'll add that on. What's the history of these algebras? So these were introduced by Artin and Shelter in the 80s, and they were studied by Artin, Tate, and Vandenberg in the early 90s. The idea is that they play the role of coordinate rings of non-commutative projective space, or that they're non-commutative analogs of polynomial rings. And I'll at least say something to justify this in the next slide. So, of course, if you want to study non-commutative projective geometry, the starting point is understand non-commutative projective space. So studying Artin Shelter regular algebras has driven a lot of the non-commutative projective geometry research in the past couple decades. So some examples. So this is one piece of justification for why you call AS regular algebras are non-commutative polynomial rings. Commutative algebra is AS regular if and only if it is a polynomial ring. So, okay, so it is a non-commutative generalization in some sense, if I require finite GK dimension. Dimension 2 AS regular algebras with finite GK dimension, there's really only two. So there's the quantum plane, where you have two generators x and y whose multiplication is skewed by some parameter q. And there's the Jordan plane, which has these relations. In general, with no assumption of finite GK dimension, James Zhang classified the AS regular algebras of dimension 2. And Artin, Tate, and Vandenberg used some techniques from algebraic geometry to classify AS regular algebras of dimension 3 with finite GK dimension. So dimension 2, there's really only two of them. Dimension 3, it's a lot harder to classify them, but Artin, Tate, and Vandenberg were able to do it. But okay, that's kind of the extent of our knowledge of classification problems. So there's a lot we don't know about AS regular algebras still. So for instance, I mean, dimension 4, so dimension 3, Artin, Tate, and Vandenberg did it in the 90s. And since then, there are a lot of examples known of dimension 4, but no classification. Or dimension 3 if you don't assume finite GK dimension. And there are a lot of algebraic properties that we don't know. So with finite GK dimension, all of the examples known are Noetherian and domains, but even a basic thing like that, completely unknown whether they satisfy it in general. But one result I want to say is that, which was, I think, originally done by Paul Smith and then was generalized by Liu, Palmieri, Wu, and Zhang, is that if you have an n-Cazul algebra A, then it's AS regular if and only if its Cazul dual is Frobenius. And okay, so the idea is generally you're AS regular if and only if the X algebra is Frobenius. So if you're n Cazul, then the X algebra sits as a subalgebra of the Cazul dual, and so you can check this property on the level of the Cazul dual. Okay, so now this result here is really a motivational result for us for this project. This was proven by Radschilders and Vandenberg, which is, suppose you have two AS regular algebras of the same dimension. Then their universal quantum groups are Morita-Takeuchi equivalent. So A and B are quantum symmetrically equivalent. And so I think the main result, one of the main results that I want to say that we obtain is a way of going backward from that result. So if you start with a connected graded algebra, then if it's Noetherian AS regular and B is quantum symmetrically equivalent to it, then B is AS regular. And then if you drop the Noetherian assumption, but you add an n-Cazul assumption, then we can say the same thing, except we also need to require that this quantum symmetric equivalence, it's not a generic Morita-Takeuchi equivalence, but it's actually a two co-cycle twist. So in this case, we can again say basically that AS regularity is preserved at the level of these comodule category equivalences. So this was already known in a couple cases. So Chan, Kirkman, Walton, and Zhang had already proved this for two co-cycle twists for semi-simple hop coactions. And Chirvasitu and Smith, I think they proved something more general involving torsors, but you can deduce from their result that two co-cycle twisting for finite dimensional Hopf coactions preserves AS regularity. So, okay, so part of the point of this is to go give a backwards direction to the Rad-Shelder-Vandenberg result. So then it follows as a corollary that we can give a characterization of AS regular algebras, which is purely a Hopf algebra theoretic characterization. So AS regular algebras of dimension n is precisely just the quantum symmetric equivalence class of the polynomial ring. So it's another way of justifying that actually AS regular algebras are in some sense non-commutative analogs of the polynomial ring. I want to say something about the proof. So the main tool we use is the relative module category. So these are graded modules for A, which are also comodules for the universal quantum group in a compatible way. The category of graded modules for A, I mean, the difficulty is that the category of graded modules for A is not preserved under Morita-Takeuchi equivalence of universal quantum groups. So all the properties that I'm talking about that are being preserved are properties of the graded module category. And that category isn't preserved at all. So for example, I mean, by the Rad-Shelder-Vandenberg result, any two AS regular algebras of the same dimension are quantum symmetrically equivalent. But it is known that they can have very different categories of graded modules. So for instance, point modules, the point modules are the simple objects in the graded category. Point schemes are some scheme which classifies these point modules. And these point schemes can be very different geometrically. But the point is quantum symmetric equivalence does preserve the relative module category. So it doesn't preserve the general module category, but does preserve the relative module category. So the idea of the proof, of course, is to show that all of these things, which are defined by the graded module category, that actually all of them can be built from something in the relative module category. So, okay, so what we show is that if A is Noetherian, then graded X can be computed from the relative module category. In the N-Kazul case, we can drop this Noetherian assumption, but we add the assumption that this quantum symmetric equivalence is a two co-cycle twist. In that case, we can replace this computation of X by a condition that, I mean, we cite the result of Smith and Liu, Palmieri, Wu, and Zhang. So we can compute everything from the Kazul dual. So then the Kazul dual is going to be a comodule algebra for the universal quantum group. And the Frobenius form on it is actually H collinear. So then we show that, in some sense, taking the Kazul dual commutes with two co-cycle twist. And this Frobenius property can be preserved in the category of relative modules when we take this equivalence. Okay, so for the remainder of the talk, I'm going to focus on a special example, which come from superpotential algebras of pre-regular forms. So here by pre-regular form, I'm going to just mean an M-linear form on some vector space V, which is non-degenerate. And there's some invertible matrix so that if I rotate all the vectors around and apply the matrix to the first one, then this form is invariant. Given a pre-regular form, I can define a superpotential algebra, which is associated to this, and an integer n. And this is, in general, going to be a free algebra generated by just the basis of V. And I just have this collection of relations for any J1 through Jn in between 1 and n, where I'm denoting F subscript just means F applied to this distinguished basis, xi1 to xim. Okay. And okay, so this is a graded algebra. We just put each xi in degree 1 And then it's a theorem of Dubois-Viollet that if you take a Cazul AS regular algebra, then it always appears as a superpotential algebra. So even though I'm focusing on superpotential algebras now, I guess in some sense it's a bigger class of algebras than the AS regular algebras that I was talking about before. So if you take two M-pre-regular forms E and F on two vector spaces, don't have to be the same dimension, then we define what we call GLM-EF to be, so it's just going to be a K algebra with generators and relations. We have two collections, so I'm going to organize these in terms of matrices just so that I can write some of these relations a little bit easier. But we have, so two KL plus two generators, so a bunch of A's, a bunch of B's, and then D and D inverse. And what are the relations? So I have a collection of relations. So here these relations are for any choice of J1 through Jm that makes sense. So a bunch of relations which involve just the A's. So pre-regular is this definition. Right, so I have a bunch of relations that involve the A's. I have a bunch of relations that involve the B's, again, for any choice of J1 through Jm. Of course, the inverse should be an inverse to D. And then I have K squared relations that involve both the A's and the B's. So I'll just write it as one matrix multiplication. This is just the identity matrix. So really just K squared relations. And okay, yeah, so I should say for E equal to F, this already appears in the literature. So our contribution was defining it for writing down a generalization of this for E not equal to F. So when E is equal to F, this was already proven by Chervasitu, Walton, and Wang that this GLMEE is the universal quantum group which coacts on the superpotential algebra AEN, as long as AEN is N-Cazul AS regular. So we define the GLMEF, and what we prove is that if this thing is non-zero, it is a bi-Galois object for these two Hopf algebras, GLEE, GLFF. And what we prove, so for n equal to 2, we can show that this GL2EF is always non-zero. So, okay, so the upshot is if you take any two superpotential algebras from two pre-regular forms, there is a Morita-Takeuchi equivalence between Hopf algebras coacting on them, which takes one superpotential algebra to the other in the category of comodules. So we can observe this recovers two previously known results. The first is that all superpotential algebras coming from two pre-regular forms are AS regular. So we can see that as a corollary of our result because the polynomial ring is a superpotential algebra. And now we've said all these superpotential algebras are quantum symmetrically equivalent. This was previously known because James Zhang classified the dimension 2 AS regular algebras, and you can look at the classification and see, okay, actually every superpotential algebra appears here. It also recovers a special case of the Radschelder-Vandenberg result that I mentioned earlier. So, I mean, we also recover all dimension 2 AS regular algebras are quantum symmetrically equivalent. So, of course, this is just a special case of their result. They prove it for arbitrary dimension. So one example, so if E and F are two, I'm going to define two specific pre-regular forms on vector spaces of different dimension, and they're just going to be basically set by the Kronecker delta. Then I can write down the relations of GL2EF. They look like this. And you can observe that this is a quotient of the Leavitt algebra, which just has generators of these two matrices A and B, and the only relations are basically that A and B are two-sided inverse to one another. Which is a foundational example from ring theory that you look at when you want to show that there's no consistent notion of rank for a free module. So our algebra is appearing as a quotient of the Leavitt algebra. And the way that you show that there is no consistent notion of rank for a free module is one shows that the Leavitt algebra is non-zero. And you do it by a Grosvenor basis calculation. So for our GL2EF, we can also do a Grosvenor basis calculation. So here's the Grosvenor basis. It's a quotient of the Leavitt algebra, and the Grosvenor basis is consequently more complicated. So I'll invite you, if you're bored during lunch, you can check for yourself that this is a Grosvenor basis. I should say this is not how our proof goes in general. So we show that GL2EF is always non-zero. We don't do it by computing a Grosvenor basis for any two GL2EF. But in this case, we can check that. Okay, so what about GLN for n bigger than 2? Well, in that case, we know that there exist superpotential algebras which are not AS regular. So we know that that this result doesn't generalize to higher n. I mean, they're going to be E's and F's, so the GLN EF is non-zero. Well, okay, for that theoretical reason, but also because we've computed examples to make sure we weren't, to double check ourselves. And we did find it, I mean, you can plug in examples and show that, you know, GL3 EF is 0 for some choices of E and F. So we don't know when GLN EF vanishes or not, but it does give us some tools for studying AS regularity. So if E is we can take the pre-regular form corresponding to a polynomial ring. You take an arbitrary other pre-regular form F. Then, so of course, something that we want to check is AFN AS regular. I mean, it's not an easy question in general. So now we've taken these homological conditions, and by the first theorem that I stated, our first theorem that I stated, we can kind of reduce these homological conditions on the level of algebra to hop theoretic conditions on the level of the universal quantum groups, or on the level of these GLN EEs. And then because we have this potentially non-zero bi-Galois object, we can, now this condition of equivalence of comodule categories is reduced to, like, I just give you an algebra with generators and relations, and the question is just, does this thing vanish or not? So I think that's everything I wanted to say.
Any questions?
General question. You were saying that these non-commutative algebras create voting categories should be part of this terms of non-commutative geometry. In that context, shouldn't you be the focus would be on graded category modular torsion?
Yeah, so that's a great point. So I think I tried to, so Artin and Zhang, when they define non-commutative projective schemes, they define it as the graded category modulo torsion. So when I think, so I was kind of sweeping that under the rug. So I think what I tried to say was something like, we only study A up to graded modulo category equivalence. As you say, it should really be up to equivalence of the modulo torsion.
So the only things I have examples
That's an interesting question, and I'm not sure about the answer. Yeah, that's a good question.
Questions? Questions from the line? that's not the case, then let's thank him again. So we just on the